Well, thank you very, very much. I think we can jump straight into the presentation. So the goal today is really to show you at a very high level what I've been working on and what you could do with these models. Is not to provide you with a holy grail. There isn't such a thing. But just to give you the framework I've been using so that maybe hopefully it's useful. So we'll start reviewing at a very high level the possible application of ML to financial markets. And then we'll be spending a little bit of time looking at supervised learning, particularly a particular type of classification model, i.e. decision trees, and see how you can use them to harvest alpha or to even construct a portfolio in an optimal way, optimal obviously not according to the modern portfolio theory, and then a few generic thoughts around risk management. So machine learning, everybody talks about it. I think it's become very, very powerful in many industrial fields and the engineering space. In the financial markets, we start seeing the very first applications, but then when you start looking at who is really using machine learning for trading or for organizing parts of the organization, you will see that it's not that many. The opportunities are obviously very, very clear. The ability of using non-parametric methods to identify complex relationship, it's really a great opportunity, not having to fine-tune a model all the time, but you simply have an object, you put it there, and the model does everything for itself. So I think that that's very, very powerful. Detecting input and output relationship, which is typical of supervised learning, it's a beautiful thing. You know what you want to achieve. You want to make money, for instance, when you construct an alpha model, and you got a set of inputs that you think you got predictive power, and you put the two things together, and your job is then just to go out and validate those relationships. We've seen today, we've heard today about the ability to model unstructured and unclassified data. It's another very powerful thing, but the challenges are there. Two types of challenges. The challenges of applying machine learning methods to financial markets. I think risk of overfitting is obviously the biggest risk we have, and it's a risk that, despite we talk about it, it's, I think, impossible to eliminate from the process. Financial data is said to be reflexive. You know, George Soros's theory is right. I mean, if you train a model to classify from the picture an animal, nothing is going to happen to the animal if it's being classified in the right way. But if you're classifying stocks into a buying opportunity or a shorting opportunity, you go out and you trade. Your action, potentially in conjunction with the action of other people, will affect the price of that security. Of course, getting your hands on data sets, I think from experience, it used to be in the old days, you had multiple sources. Then Bloomberg has done a phenomenal job alongside many other data vendors in sort of classifying, mapping the data, and providing the data through an API to our desk. And then now we have multiple other data sets, and we go back to the problem we had 20 years ago. And then, of course, the challenges when it comes to modeling financial time series, the fact that you're dealing with non-stationarity, the fact that the property of the distribution changes over time, the fact that you've got serial correlation, cross-sectional dependence. So think about the application. Something happens to a tech company, all the other tech stocks are going to react based on that, even if the news was not referred to them. So I think these are the challenges that you need to bear in mind. And here, this is how we are sort of classifying or depicting, if you want, machine learning, so unsupervised, supervised, and reinforcement learning. Earlier, we heard a beautiful presentation about how to use reinforcement learning to predict the delta of an option contract. I personally find reinforcement learning incredibly difficult to use, not really reliable. One thing of these models is just they're beautiful when you read the theoretical framework. You set up the environment, an agent. The agents got rewarded by trading, let's say, in the right way. But these models takes forever to train compared to unsupervised and supervised learning, which are talking about seconds, minutes. I remember the applications that I did. It took my computer over 2 days to find something, and the results were okay, but I didn't feel it was a valuable thing to do. And when you talk to the gurus in this space, you ought to hear, I always hear a binary thing. Either these models are not working, and so there is no point writing about it, or you hear these models are too good, and we can't write about the IP either. So I'll let you choose in which camp you want to sit, but my experience has been sort of mixed. Unsupervised and supervised instead, I think it's very powerful what you could do with these models. Unsupervised, we need to bring everything into machine learning definition today. So dimensionality reduction is one of the things you could do. PCA, obviously, is one of the things that you could do. I remember when I started in Germany working for a German bank at the very beginning, using it to look at looking at the Bund and how you could decompose it and try to find correlations or similarities with macroeconomic factors. You got clustering, the ability of grouping objects by similarities. This is really the high multidimensional space. I think it's great. I think you can use you can use these models for a variety of things, not just trading, but in my life, I came across many analysts that had to come up and maintain an investable universe for fund managers. And that process is very random. They either get a tap on their shoulders by the PM saying, I'm interested in these specific stocks, can you please do some work on it? Or they come up with a name by reading the Financial Times or any other sources, but it's completely unstructured. But what if the analyst has got, for instance, companies that he or she likes, and then you look for similarities with other companies around the world? You may be able to come up with a more robust way of creating investable universes. So again, there is nothing done at this level, at least from what I've been seeing, and I think you can use clustering very, very well there. Supervised learning, obviously, you got the two camps, the regression and classification. Regression, you're in the neural network space. I've been working with these models since university, and I'm not really using them. I find them very unstable, very difficult to prove and validate. You get fantastic results when you expand the size of the problem, and then, which of course is not readable. It's very difficult to understand what the model has picked up. And when you make them too simple, they don't really work. And possibly how you set up the problem is a problem in itself. I've always tried to predict tomorrow's return or the return over a period of time. And then maybe that task is impossible. Maybe one can use it, for instance, to filter noise from a trend. Maybe you could use it to do smarter things than just predicting. And classification, I find classification model instead very, very useful. Obviously, I've been using them to classify situations into a buying or into a selling opportunity. We'll see an example later on. But I think if you have a touch of imagination, you can really try to construct even optimal portfolio using these models. So decision trees are very popular. They are another similarity with the other modeling is that these models are very old. I think the first paper on decision tree came up in 1984, and they were used to resolve a very specific problem in the States, how to hospitalize the patient. So the patient was coming in with some specific symptoms, and the model was able to allocate them in the right department, which I find it very useful because you can follow that logic and then apply it, for instance, to the financial markets. Decision trees, though, they suffer from instability. Through ensemble learning, you're able to sort of correct for that, but they're really very sensitive. So we always say trying to reproduce the same results over periods of time is what you need to try to do. I think it's really very difficult to do it. So my approach is really never trust one model, try to put multiple models in parallel, and then try to diversify the modeling to get better results. So overfitting is obviously a problem that, as I said, I don't think you can get away when you do this. On the left-hand side, you have a very simple attempt of a linear model to try to fit what is non-linear, and so you got an underfitted model. On the right-hand side, you have a model that apparently was able to predict everything, fit everything. That model most certainly has not learned any relationship, but has been able to memorize all those points, and then when you put it out in production, you see that it doesn't work. I often present an example, a joke, by trying to predict Apple shares using the weather readings in Los Gatos, hometown in California of Steve Wozniak. And I can show that by taking the temperature, the humidity, you can perfectly predict in the in-sample period, obviously, Apple's direction the next day. But then when you put it into production, you get nothing. So garbage in, garbage out. In the middle is really where you want to be. And to be in the middle, there are 4 things that you could do. Cross-validation is obviously the very first thing to do. So trying to decompose your training set into smaller periods so that the model is able to focus and tune those parameters in smaller subsets. Again, you've got different techniques here. You need to be careful with financial time series not to remove the sequence, and therefore you need to use the right approach. Regularization is basically forcing a model to be very simple. Again, these are numerical techniques that will do it for you. Ensemble learning, wisdom of the crowd of Aristotle, is suggesting that actually, if you're able to diversify your model, you will tend to get a better outcome, better results. And then playing with features is another thing you can do, i.e. trying to remove them or try to combine them. Again, you can use numerical techniques to do it. I like to be in control of the features that I'm using. Therefore, I think it's better to do the exercise yourself, but you could trust the model for doing that. Now, in the interest of time, I'm going to skip the next few slides. So a very simple example, how to try to use these models, decision trees, to sort of improve very simple trading strategies. Back in the 80s, moving average crossover was very popular, was used by commodities traders. You were comparing the last price with a moving average over a period of n days. And if you had to sort of depict that trading rule into a decision tree framework, that's how it would look like on the left-hand side. If the ratio is greater than 0, you go long. If it is shorter than 0, you go short, if you're allowed, obviously, to go short. And I've applied that to Apple using a 5-day time window. And you can see that since the 90s has produced a -8% per annum. Now, as a quant, typically my experience is like you don't like the outcome of a model, you just throw it. You just say the input has got no predictive power, let's move on. But using decision trees, you could try to improve that. Now, if you try to keep the tree very, very shallow and you can go through it, maybe the problem is not on the indicator that you're using, but maybe it's on the logic that you attach to the indicator itself. So again, it's not a perfect example, but what you see right there on the right-hand side is an out-of-sample result of improving the 5-day moving average with the yellow line. It's a model that, would I be treating it? Maybe in isolation, not, but in conjunction with other models, possibly yes. The other thing that you could do with decision trees is, for instance, detecting patterns between inputs. If you believe that your time series that you're trying to predict on the right-hand side can be affected by its performance over the past days, I can tell you right now, for instance, a good example is Bitcoin. There is a very strong relationship between how Bitcoin is performing in the short term and how it performs the next day. You could try to get these inputs into a decision tree and try to see if they got any predictive power. So I've done that. This is the outcome. We're still applying this to Apple shares. And what you do see here, the red line is the in-sample period, the out-of-sample is the white line. Again, think about the combination, for instance, of this model with the previous one. By adding multiple models together, you're able to sort of diversify and get more stable results. The other beautiful thing of decision trees is that you don't need to apply the tree completely. You can just follow certain branches. You can dive into, test them, and see how they are performing, and then decide yourself if you feel comfortable with that specific rule. Now, constructing an optimal portfolio is not optimal, as I said, under the modern portfolio theory, but I gave myself this exercise to build an asset allocation model by trading 12 US liquid, US listed ETFs, equities, bonds, commodities, the classic ones managed by BlackRock, State Street, the very liquid one, and the front month VIX future as a proxy of hedging for your market risk. The goal is to achieve a long-term capital preservation, what most asset allocation models should be doing. And ideally, I like to achieve low double-digit annual returns, coupled with low volatility and shallow drawdowns. Now, philosophy, I think from what I've seen, if you are able to rebalance your portfolio more frequently, then your risk-adjusted returns tend to be better on average. Although you may incur into transaction costs and fees. Transparency is really very important. Therefore, try not to build too complex strategies, too complex systems that you're not able to understand what they do is another thing that you should do. And the intuition here is really that the allocation shouldn't be driven by the expected returns, by your alpha, but should be driven by the amount of risk in the system. And so by doing that, I basically had to collect inputs, which I think got predictive power. And so I've decided to go down for the VIX index and the rate of change of the VIX over 5 days. So those are the only two inputs that I'm allowing myself to use. I'm then need to get an outcome. So I need to map them against something. And I want to know how risk assets are performing. So I'm checking the S&P 500 direction. S&P going up, I give a +1. S&P going down, I give a -1. And then I try to have a diversified approach on how I construct the trees. Now, by doing this, I've mapped the two inputs that I'm using, the VIX and the rate of change of the VIX over 5 days. And I came up and I mapped them against the S&P 500 going up or down. And this is the outcome that we got. Now, the problem is that from this stage to the allocation, there is a step that you need to do. So if the VIX is telling you that you should be on a risk-on mode, what kind of allocation shall I be using? Well, by here putting together this table, sorry if you can't read it, but the idea is very simple, is to say whenever the decision tree is giving me an outcome, I can always go a step forward and see how the asset classes perform. And so if I got a binary outcome from the tree, which is basically risk on or risk off, I can extract from the historical data sets only the relevant period. So in this case, the output of the decision tree would be risk on or risk off. I can extract from history, the distribution, how those returns were behaving, how the risk, and derive an optimal allocation. For this example, I've done a very simple case. I constructed the Sharpe ratio of each individual securities in those two phases, in those two regimes. And then if the risk-adjusted returns were negative, I gave a 0 because I can't go short. And if it is positive, I made sure they all add up to 100. And if you do that, that's sort of out of sample what we got. It's not really what I really was hoping to have. This year obviously has been relatively bad, -14%. But bear in mind that, of course, being a long-only strategy, you rely on securities being able to go up. And when I look at the performance of traditional, very simple, the 60-40 model or traditional multi-assets, the numbers are, tend to be even worse than this. So final thoughts on risk management. There's a lot that you can say about it. There are many aspects of machine learning, particularly you should be talking about risk management, about many of its aspects. Here I've taken a very simple example. Very often we tend to build a model, back-test it, stress-test it, understanding what it does, and then we put it into production, and then inevitably the model doesn't work. And the model starts losing money, and what do you do from there? So what I've tried to do here is just to show you that even when you have a good Sharpe, a Sharpe of 2, a risk of 6%, and an expected return of 12%, you can still have periods when that line is going down. Therefore, what we are aiming to do when we build a model is obviously try to mimic the green line. That's where we're trying to be. We try to have a strategy that is consistently delivering positive returns with effectively no risk. Now, if you run multiple simulations of that blue line and you're assuming there is a positive correlation of 0.2, because everybody's able to show negative correlation, but I've never been able to produce negative correlation among strategies that I come up with, because if it's me, the source of the intuition, it's likely that all my intuitions are somehow connected with each other. But here I wanted to show that even if you have a positive correlation of 0.2, when you simply blend those 20 strategies together into one by equally weighting the results every day, you effectively get on the green line. So think about diversification when you build a model. Don't try to sort of overly complicate it, fine-tuning, refitting it, retraining it, Try to sort of look for complementary models that can help removing risk from the table. And so very easily, I think the advantages we touched upon earlier are very clear. I think the reason why everybody talks about ML is because ML is actually working, and I strongly believe that that is the case, but you need to be very careful because there are many risks associated with that. I think the risk of overfitting remains the biggest risk to tackle. Understanding your model, correlation versus causation is another problem that you often have when it comes to application of these models. And decision trees compared to neural networks are very simple to use, and they can be applied really in a variety of ways. Now, I run out of time, so I thank you for your time and your attention. Thank you.